Hi, my name's Adam Roach, and I'm a principal engineer at Caffeine TV. Today I'm going to go over some of the things that we learned implementing an ingest gateway for low latency broadcasts. So first, a quick introduction for those of you unfamiliar with Caffeine. We're a live-first social media company founded in 2016 with a focus on culture, sports, and music. We host a mix of produced studio shows and user-generated content. And one of our key differentiators is that we provide support for very rapid interaction between viewers and broadcasters, which means that we need end-to-end media transmission of far less than a second. When we first launched, our broadcasting stack was entirely WebRTC, since that was the best way to get the absolute lowest latency possible. To get to launch quickly, our initial real-time CDN was built from a lot of pre-existing products like Janus, FFmpeg, MediaLive, and Zixi, all coordinated by a lightweight set of orchestration servers. And the core of our real-time CDN is a high-speed multicast-based packet switch, which simply passes along the incoming stream verbatim. Over the years, we've learned, sometimes the hard way, that fanning out a single WebRTC broadcast to hundreds of thousands of viewers is tricky and expensive. So some of our larger broadcasts, the ones where little extra latency won't be noticed, have started using low-latency HLS as an alternative. One of the other things that's been challenging is that there are no off-the-shelf broadcasting tools available for WebRTC. So we've begun experimenting with SRT, which has good and growing support in the tools that our broadcasters use. Historically, we've maintained our own fork of OBS with added WebRTC support, but keeping on top of OBS's release schedule is very resource intensive, and our users get frustrated when we fall behind. The OBS project has announced an intention to support WebRTC with the emerging WIP protocol, but the timeline for that is probably still some ways off. So let's get into the rewrite. There are a couple of factors that drove us to rewrite our media ingest from the ground up. First, Caffeine has seen some really good growth over the past few years. Last year, we started bringing on a lot of new producers who would sometimes send us streams that are pretty far out of spec compared to what our systems were designed for. For example, our egress node capacity is dimensioned with an assumption that streams are no larger than 5 Mbps. And we had one new producer send us a 12 Mbps stream on their first broadcast, and this didn't go well for our network, didn't go well for their viewers. Second, maintaining professional broadcast tools is a distraction from our core value proposition, and one that other people are doing a fine job with. We really want to leverage industry-standard broadcasting tools without having to perform extensive modifications. And to do this, we need something that can ingest media in forms other than WebRTC, and then convert it for our own CDN. As I mentioned earlier, and like many digital broadcasting networks, we have several load-bearing instances of FFmpeg in our network. And we could have used FFmpeg again as part of transforming media into WebRTC for our network's core. FFmpeg is an awesome tool, but it also presents some challenges, especially in live broadcasting. First, as a command line tool, FFmpeg presents significant challenges to get properly configured, especially because implementation doesn't always match documentation. And while the things that you can tell it via command line are impressive, they're not exhaustive, and we found many workflows where we end up compromising what we actually want to do because there's no way to tell FFmpeg how to do it. FFmpeg also has some unfortunate edge case behaviors. For example, if you send FFmpeg a media stream over a lossy protocol like WebRTC, and then write it to a reliable channel like CMAF or a file, then packet losses make it lose AV sync, sometimes quite badly. Finally, FFmpeg isn't always spec compliant in some frustrating ways, one of which I'll touch on in a little more detail later. And so, because of these various factors, we began re-implementing our ingest gateway in earnest earlier this year, which went live in late August. And to allow for a phased rollout, the gateway implements the same network API as our existing orchestration servers. We decided to write it in Go, primarily because most of our microservices are in Go, and so we have a fairly large pool of Go expertise in the company. To get our new ingest gateway deployment ready as quickly as possible, we incorporated many open source components like the Pion WebRTC stack, AVlib, Hivision's Go SRT library, Cisco's OpenH264 library, and Comcast's GoTS library. Internally, the gateway is implemented as a highly modular media processing graph, so we can incorporate new components as new protocols and needs arise. And some substantial portion of that processing graph is a transcoding engine that lets us build bitrate ladders, convert audio formats, and provide future capabilities like the ingest and/or transmission of AV1 video. With that as background, I'm going to go over 4 interesting things that we've learned along the way, followed by a slightly deeper dive on one of the more perplexing challenges that we came across. All right, thing one. So, as I mentioned earlier, FFmpeg has some annoying issues when it comes to spec compliance. And here's a specific one that caused us some grief. When you transmit media using SRTP, which we use when relaying streams from one processor to another, there are two cryptographic operations involved: encryption and signing. When you set up these SRTP connections, you signal which cryptographic algorithms to use with a named profile called a crypto suite, which are defined by IETF RFCs and registered in this table here. Some of the links in our network use the AES CM128 HMAC SHA-132 crypto suite, which is a mouthful, between our ingest and their destination. When we initially implemented this in our new ingest gateway, we found that we were getting tons of cryptographic signature errors on the receiving side, which was an FFmpeg process. We finally determined that these were issues verifying the SRTCP messages that we were sending, and it took reading FFmpeg's source code to figure out what was actually happening here. So, a little more background on crypto suites. Among various other things, crypto suites define the number of bytes used to sign an SRTP packet, and as a separate parameter, the number of bytes used to sign an SRTCP packet. For this particular crypto suite, the signature for SRTCP is defined to be 80 bits or 10 bytes long. And after a lot of other troubleshooting, we finally tracked down the code in FFmpeg that initializes signing parameters based on the specified crypto suite, and discovered it uses 4 bytes instead of 10 for SRTCP packets for this particular crypto suite. And there are actually several things wrong with the code in this slide, but that's the one that ended up biting us. So we were able to work around this in the ingest gateway by simply removing the final 6 bytes of each SRTCP packet that we sent. Now, if we had to receive media in this format, it'd be a lot more of a problem because we can't magically synthesize that last part of the signature, but it ended up working out for us this time. In general, when we find issues with open source software, my inclination is to contribute fixes back to the project rather than trying to work around them. But in this case, that wasn't really feasible. FFmpeg has been broken like this for over a decade, and so other implementations are similarly broken just so they can work with FFmpeg. For example, we know that at least some Janus plugins have implemented this non-standard version of this crypto suite, and there's no way to fix FFmpeg without breaking those plugins as well. All right, thing 2. We've been able to find Go libraries, or Go bindings to C libraries, for most of the third-party components that we want to use, and this has generally been a winning strategy. One of the things that we need is a media processing library. An AVlib, which is the core media and processing library used by FFmpeg, is probably the most full-featured library available. If you go looking on GitHub, you'll find there are a bunch of projects in various states of development that look like they should be general-purpose bindings for AVlib in Go. On a closer look, none of these bindings implement the full AVlib API, which is huge, so that's completely understandable. But we could only find one that appeared to have all the functionality that we need for our current and future plans. So after running with that for a while, we became frustrated by a lot of violation of Go's idioms, and in particular the fact that it doesn't use finalizers for resource management, which requires a lot of cumbersome memory management in our Go code, and you don't typically do memory management in Go code because it's a garbage collected language. We also suspect there might be some memory leaks baked into the binding, but it's hard to know for sure because, again, it pushed a lot of memory management into our code. So ultimately, we decided to jettison the third-party binding and write our own, which covered the parts of the API that we know we need to use. Once we put the basic framework for a binding in place, adding new API surfaces has been quick and easy, and we've been far more confident in proper resource management. In practice, I don't think we're unique in this regard. Because the large API surface of AVlib, it's pretty unlikely you're going to find a third-party binding that meets all of your needs. So if you find yourself in a similar situation, definitely evaluate writing your own language bindings alongside any other options that you consider. A third lesson we learned is that the level of effect support in WebRTC is not where you might expect it to be nearly 10 years after Chrome and Firefox released their initial implementations. One of the things that we had hoped to do with the new ingest gateway is improve video quality under conditions of moderate network loss. And the WebRTC specifications do say that video streams should be sent using FlexFec, which would accomplish this. In practice, the webrtc.org library, which most WebRTC clients use, including ours, appears to have support for receiving FlexFec, but it doesn't have support for sending it. It does also seem to have support for an older technique called altfec, which we plan to implement, but it's not clear whether there's any way to turn it on in web browsers, so it may be limited to use in our native clients. The final high-level lesson learned is that framing of H.264 video in RTP streams is a bit of a mess. The spec says that senders should mark the packet that contains the end of an H.264 frame with a marker bit so that receivers know when to send it to the decoder, but it also cautions that decoders can't rely on this bit being set. And in practice, it frequently isn't. The problem is that doing 100% compliant packet reassembly, in this case, requires your RTP layer to fully parse the H.264 bit stream to find out when a new frame starts. And that's a little bit bonkers. So in practice, it appears that everyone uses some set of heuristics to find frame boundaries in RTP, but I've yet to find anywhere that writes these heuristics down aside from in code itself. So to get this right, we ended up examining the logic used by GStreamer and implementing the same heuristics so that we don't have to reinvent this wheel and find corner cases in the wild. All right, now I want to dig a little bit deeper into sort of the boss level challenge that took us probably the longest amount of time to figure out, especially because the symptoms are kind of counterintuitive relative to the root causes. When we were very first starting to roll out our gateway and put a small percentage of our traffic onto it as part of a phased rollout, we saw a number of videos, mostly from mobile devices, that had a pretty distinctive flaw. At apparently regular intervals, they would briefly pause and then suddenly jump forward. Here's an example. We were able to reproduce this behavior using a metronome, which made it obvious that the pauses were exactly 2 seconds apart, which is the same as our keyframe interval. We pursued a bunch of theories to try to track this down, including adding a way to bypass the transcoder pipeline on the theory that maybe we were taking too long to encode keyframes or something like that. And we added a mechanism to simply forward receive packets instead of trying to dejitter them or do any other processing. But nothing we tried made the problem go away, even when we were basically acting as a simple packet router. So just a quick note on video frame types to make sure folks can follow the rest of this explanation. Video frames consist of a number of different frame types, which can be roughly broken down into keyframes, which contain an entire image, think like a PNG or a JPEG, and non-keyframes, which describe how to change the previous frame into the current one. In a typical video stream, keyframes are about 2 to 4 times the size of non-keyframes. For example, here's a graph I grabbed of the ratio of keyframe sizes to non-keyframe sizes for one of the streams in our network. And you can see there's a fair amount of variability. Most of that depends on how much motion there is in the video. And so, after the various troubleshooting steps that I described, we finally came across a GitHub bug that described a curiously similar problem in an entirely unrelated piece of software. What they determined was that the problem only arose when the keyframes became very large, which counterintuitively only happens when there isn't much motion in the video. And then we were able to confirm that this was at least plausibly the same issue we were seeing by putting a large moving scene next to our metronome, and when we did that, the problem completely disappeared. It turns out that what we're seeing arises from the interaction of a couple of different systems. First, when you set up a video encoder, you typically give it a bitrate budget that represents the bandwidth you want the compressed stream to take up. The encoder then uses up to that many bits to encode the stream, ideally with the best quality possible within that constraint. When there's not a lot of motion in a video, the non-keyframes don't have to say a lot, so they end up being very small, consuming almost none of that bitrate budget. This means that when it's time to generate a keyframe, the encoder has a ton of budget left over, which it immediately spends on making a very nice-looking, very large keyframe. And where that becomes a problem is when the client goes to send this extra large keyframe in RTP, because there's not inherently any congestion protocol for RTP. Implementations almost always pace out their RTP packets to avoid overwhelming the network, which would cause many of the packets to be dropped. And when you have a single keyframe that takes a lot of packets to send, that can take a while. How long's a while? Looking at a low motion stream in our network, we see these large keyframes taking nearly 1/3 of a second just to be sent across the network, or nearly 10 times as long as they're actually supposed to be on screen. So let's put all this together then. By the time the last packet in one of these extra large keyframes shows up, it's about a quarter of a second too late. This means the video has been paused for that long, which is extremely noticeable. And then the non-keyframes that were in line behind that jumbo keyframe all show up at once and are quickly decoded and make the video jump forward to where it's supposed to be. So that's what we've been seeing. How do we fix this? Well, on the receiver side, the only thing you can really do is to increase the size of the jitter buffer as a way of adding an artificial broadcast delay that gives these jumbo keyframes time to finish showing up. This is pretty suboptimal for us because it means that we're inching closer to blowing our sub-second end-to-end goal. Luckily, because we know that this is caused by this specific issue and we can measure exactly how big the impact is, we can make this delay adaptive so it only happens on low motion streams, but that's still far less than ideal. Longer term, we're going to be doing some tuning on our broadcast clients to address the issue, which will allow the additional delay to be much shorter. First, most encoders have knobs that you can turn to adjust how much of a time frame they consider when they're building their bitrate budget. And by making this window much smaller, we can reduce the amount of excess budget available when a keyframe shows up, which should rein in how large they can grow. Finally, we've determined that the packet pacing for the version of the webrtc.org library that we're using may be overly conservative in its packet pacing, so some of this may get better the next time we upgrade to a more recent version of that library. And as a final footnote, I want to point out that once you understand the general shape of this problem, you can probably start seeing it arise elsewhere. For example, we had an historical issue where we'd get unexplained packet loss and visible video defects when we were sending low motion videos through a certain third-party video processing service. And although we haven't been able to go back to confirm that jumbo keyframes were the cause, since we've long since worked around the problem by using a different encoder, the problem entirely fits with what you might expect to see if you generate very large keyframes and then try to send them all at once without any RTP pacing. Periodic massive packet loss when there's not a lot of motion in the frame. So that's a brief survey of what we learned over the course of implementing our low latency ingest gateway. Thanks for joining us, and I look forward to your questions.